I'm Jeroen van Meij and welcome to my lecture series on computer and network security. In the previous video, it became clear that insecure use of public keys can lead to man-in-the-middle attacks. As such, whenever public keys are used, their authenticity should be verifiable to ensure the public key has not been altered. In this video, I will zoom in on different techniques to securely share such public keys. There are four main methods that can be used to distribute public keys. The first one is public announcement. It's very straightforward, and the party that wants to share its public key basically just broadcasts it to others. The second one is a public directory. Here, a centralized directory is maintained where anyone can upload their public key. The third one is a public key authority, which is like a central directory but tightly controlled by a trusted third party. Finally, the fourth method are public key certificates, which are a decentralized way of secure public key exchange. I have a question for you. Which of these four public key distribution techniques are most robust to attacks? Multiple answers can be correct. Feel free to pause the video if you want to think about it. And let's take a look at the correct answer. The correct answer is both C and D. A and B are not very secure. And in the remainder of this video, I will show you why. Let's take a closer look at the public announcement. In this method, the party that wants to share his public key will just send it to anyone that wants to receive it. However, there is not any type of control, which means that anyone could forge the announcement and pretend to be A, spreading their own public key. As such, this method does not protect against the man-in-the-middle attacks I talked about in the previous video. The second method of public key distribution relies on a publicly available key directory, where anyone can register their public keys. This can be done either in person or some other secure authenticated communication method. Obviously, the public key directory needs to ensure that any registered key is authentic. However, this approach has some downsides. If, for example, the directory's private key is stolen, an attacker could counterfeit public keys and impersonate others. A more secure approach is a so-called public key authority, which provides tighter control over the distribution of public keys than a public directory. Here you can see a typical public key authority scenario. In this case, the initiator A will send a request with a timestamp T1 to the public key authority. This request does not need to be encrypted. The authority will use its own private key PR-auth to encrypt a message sent back to A. This message contains the public key of B and the original request and timestamp. Anyone with the public key of the authority will be able to decrypt this message, but that's not a problem because it serves the goal of authentication. When A decrypts it, it knows that the message originated from the public key authority. And the message contains the authenticated key, public key of B, as well as the original request to ensure it was not tampered with while being transmitted, and the timestamp to ensure this is not a replay attack. Subsequently, in step 3, A will encrypt a message to be sent to B using the public key of B. The message contains its own identifier and a unique nonce. B will be the only one that is able to decrypt this message because you need the private key of B to decrypt it, and can then see that A wants to exchange public keys with B. B will send a similar request with a timestamp to the public key authority and receive back a response with the public key of A. At this point, both A and B have each other's public key, but they have not done two-way authentication. This is done in the last two steps, step 6 and 7. First, B will use A's public key to send back the nonce N1 and also send a second nonce N2. A will be able to decrypt the message with its own private key, receiving back nonce N1 and knowing now for sure that it's communicating with B. A will also encrypt the second nonce with the public key of B and send it back, so B can also authenticate A. This approach is more secure than a directory, but is still vulnerable to some tampering in the public key authority servers. Moreover, it requires every party to communicate with the public key authority whenever it wants to retrieve another party's public key. So there is here a scalability bottleneck due to the fully centralized nature of this approach. And this brings us to the fourth and last method of exchanging public keys, namely certificates. And certificates get rid of the requirement of having to contact a central authority to obtain a public key. Instead, the central authority is only responsible for creating the certificates, which afterwards can be freely exchanged to exchange public keys. So a certificate consists of several types of information. It contains a public key, the identifier of the owner of the key, and a signature of the trusted third party, in other words, the certificate authority. And anyone that obtains a certificate should be able to determine the name and public key of the owner. They should be able to verify that the certificate indeed originated from the certificate authority and was not counterfeit. Only the certificate authority should be able to create and update certificates, and anyone should be able to verify if the certificate is valid, given the limited lifetime of a certificate. And let's take a closer look at how these certificates actually work. The first step is to obtain a certificate for your public key. So let's say an entity A wants to certify their public key PUA. They will send this key to the certificate authority together with proof of their identity. For example, this could be done in person. The certificate authority will create a certificate using its own private key, PROUT, and it will attach a timestamp, an identifier of A, and the public key of A. Since this information is encrypted using the authority's private key, no one is able to change it, but anyone with the authority's public key is able to verify it. The same can be done by another entity, B. The timestamp is added to ensure that the validity of the certificate can be checked, for example, if it has a limited lifetime. The second step is exchange of public key certificates. In this case, the public keys can be safely exchanged without fear for a man-in-the-middle attack between two entities by sending the actual signed certificate. The certificate cannot be counterfeited by a man-in-the-middle because the man-in-the-middle does not have access to the private key of the certificate authority. Yet, no central third party is involved in the actual exchange of public keys. As such, this approach is more scalable than the use of a central authority for key exchange, and also does not run the danger of a man-in-the-middle attack. In the next video, I will explain more details about certificates.